This is June 09 again, and paper 2. So they had more electromagnetism stroke electromagnetic induction on paper 2. So it does always seem to appear in paper 2, electromagnetism and electromagnetic induction. But be aware that some of the first household electricity stuff actually appeared on paper 1 last year. So you just can't take the risk of leaving it out from paper 1. Right, this is the electric bell question again. Explain why the hammer moves towards the gong when the switch is closed. So this isn't just as long a question, it's only worth 2 marks there. So we're looking for 2 points. So when the switch is on, the electromagnet, I'm just writing it as EMAG, is switched on or is magnetised. I'm just going to write on. And what does it do for the hammer to hit the gong? It attracts the armature, which is probably made of iron. I'm just going to write an iron armature. Okay, the springy metal strip does 2 things. So the springy metal strip is this here, this little bit is attached here, and it does 2 things to allow the current or to allow the bell to work. What are they? Well, the first thing it allows it to do is, first of all, it conducts electricity. Okay, so you can see that's part of the circuit. Whenever this is all on here, you can see that this is part of the circuit, so it conducts electricity. And the other thing it allows it to do is it allows the arm to move, the iron arm to move towards the magnet or the coil. It also allows it to spring back as well. I'm just going to write that in there. Okay. And then the last question says, explain fully why the bell might not work if the coil didn't have a core. So you can see there's the core. Now the core is generally made out of iron. Iron is a magnetic material, and that iron allows or intensifies the magnetic field in the electromagnet. So the problem would be the bell mightn't work because the electromagnet isn't strong enough, and you need it to be strong enough to attract the iron arm over. Or the armature over. So we're going to 2 marks again. So the coil may not be, or the coil's magnetic field may not be strong enough to attract the arm. I'm just going to write towards it. So, might not be strong enough, there's 1 mark, and to attract the arm, 2 marks. Okay, state 3 changes that might make it possible for the bell to work with a coil that did not have a core. So what other things could you do to make your electromagnet stronger? So you know, of course, that you could use more coils. You could use a higher current in the coils, and that would make it stronger. I'm just going to write I there. You could move the coil and the arm closer, or you could use a weaker spring or a weaker springy metal bit. So any 3 of those, there's 1, 2, 3, any 3 out of 4 will get you your 3 marks. Part B. Below is an incomplete drawing of the magnetic field produced by an electric current flowing in a coil. The direction of the current flowing in the coil is shown by the arrows. Label the north pole of the coil N. So you have to have a wee look at the direction the current's flowing in the top of the coil there. Use your right hand rule as usual, and you can see if you put your fingers up over the top of the coil there that your north pole must be down in this end here, and the other end is south then. Complete the 2 magnetic field lines that have partly been drawn and mark their directions. So you're going to get a mark for completing the 2 loops right inside, and then another mark then for putting on the correct directions out of the north into the south. And the last says, draw a third magnetic field line and mark its direction. And the most obvious one to draw is one down the middle. And those three in the middle should be parallel to each other, out of the north into the south. And if you didn't mark its direction, you wouldn't get that mark. Part C. A flexible wire set up at right angles to a magnetic field is shown in the diagram below. Describe fully what happens to part of the wire in the magnetic field when the electric current is switched on in the wire. Now, first thing you look for in this wire is there a power supply or is it a meter? If it was just a meter here and there was movement, then you would be expecting electromagnetic induction, but there is already a power supply, so that means that there is a current flowing through this wire. So you have a current flowing through a wire and you have a magnetic field that it's placed in. Now the wire itself, of course, has got its own little magnetic field in a circular direction. So in between here, that is going to cause an a magnetic field there to interact with the magnetic field of the magnet that's already there, and that's going to cause a force. So the wire is going to experience a force which will cause it to move. Now there's really only one direction it can move, one or other, and that's either up or down. Up or down. You can't see the up or down. So experience of force, that's one mark, and then the direction of it, up or down, is one mark. Here's this question coming up again, so it's come up almost every year. What is the difference between AC and DC? 2 marks. So you must explain AC and you must explain DC. AC, current which continually changes direction or repeatedly changes direction. So that's, you're only going to get 1 mark for saying both of those. And I would always put in there from plus to minus. Then DC then is current which flows in one direction only. Okay. Name the process involved in the generation of AC, and this is the same question again. Electromagnetic induction. And again, that's come up almost every year as well. Okay, so this is just to show you the difference. You look and see on this diagram, there's a power supply. And that power supply is going to cause a magnetic field around the wire, and then when it's placed in another magnetic field, then it's going to experience a force up or down. If this had been a meter and it suggested that there was a movement here, then you would be inducing current on the meter.